The following is an explanation of example 5.4 off of page 196. In this problem, we have a sample of gas at 15 degrees Celsius and 1 atmosphere, which is contained in a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? This right here is a Charles' Law question. Charles' Law, quite simply, can be written as volume equals some constant times temperature. However, as with any temperature in this chapter, we need to convert it to Kelvin. So let's go ahead and do that with both of our temperatures. 15 Celsius plus 273 gives us 288 Kelvin. And then we have 38 Celsius plus 273 equals 311 Kelvin. It's always a good idea to just go right ahead and convert those temperatures into Kelvin immediately. That way you don't forget. Now, Charles' Law is useful only when you have two specifications. The first one is that your pressure is constant. In this example, we start out at 1 atmosphere of pressure and end up at 1 atmosphere of pressure, so our pressure does remain constant. The other stipulation we must make is that our number of moles is also constant. The only time where the number of moles would not be constant is if the question were to be worded in such a way that implies or directly says that you're adding gas or removing gas. If you're adding stuff or removing stuff, you're adding moles or removing moles, and then n would not be constant. But in this explanation, in this question, n is constant. We're allowed to use Charles' Law. But I want to get it a little bit more useful. The things I care about are our temperature and our volume. And Charles' Law right now has the temperature and volume separated. I want them to be together. So when I do this, I'm going to just do a little bit of algebra and get volume divided by temperature equals B. Now, no matter when I look at this gas, I could look at it when it's at 15 degrees Celsius, at 38 degrees Celsius, at 138 degrees Celsius. No matter when I look at it, the beauty of Charles' Law is that this B is constant. So, V1 and T1 are equal to V2 and T2. So our volume divided by temperature at the beginning is explicitly equal to the volume divided by temperature at the end. So let's go ahead and plug some stuff in. We get a 2.58 liter volume at the beginning divided by 288 degrees Kelvin equals our volume 2, that's what the question's asking us for, divided by 311 Kelvin. A little bit of algebra and we can solve for V2. And V2 is equal to 2.79 liters. And let's think about it. We have a gas that starts out at this temperature and ends up at this temperature. That means that the temperature has increased. When the temperature increases, those gas particles start moving around faster. They're hitting the sides of, in this case in my mind, it's a balloon. They're hitting the sides of the balloon faster. As they're hitting the balloon, they're making the balloon get bigger. So our volume ends up being a little bit bigger than our original volume. And it is 2.79 liters. I'm not sure why I wrote a 7 there. This is useful if and only if we have a situation in which pressure is constant and the number of moles is constant. If the pressure changes or the number of moles changes, we cannot use Charles' Law. But there are still a lot of examples where the pressure and the number of moles will remain constant.